The easiest way to do it is something like this. I'm going to put x to the n because I don't know what goes here. You know what? I'm going to go out on a limb and say it's quotient. You guys okay with that? I don't know. I'm just taking my chances that I think it's going to be a quotient. I don't think everything's going to cancel. And then I write plus dot, dot, dot. Okay. I wrote all this stuff I need. And by the way, when the question is asked, how many terms do you need to see a pattern? The answer is always yes. As many as it takes. What do you notice about the very top? What do you see? 1, 3, 5, 7. Do you see a pattern of odds?
Yes.
Can I take advantage of that? Yeah, in fact, it's perfect because look at the exponent. If we're starting at 1 and we're ending at 2n minus 1, when n is 1, that gives us a 1. When n is 2, it gives us a 3. When n is 3, it gives us a 5, and so on. Then this would be 2 times 4 minus 1. Oh, this would be 2 times 3 minus 1. So I certainly am ending at 2 times n minus 1. So now let's just look at the pattern. It appears that I'm going to have 1, 3, 5, all the way up to 2n minus 1. It definitely appears that I've got that going for me. Oh, but they're all over 2. How many of them are there? N of them? Is that my numerator right now? Stare at that for a minute. 1 half, 3 halves, 5 halves.
2n minus 1 to the n halves.
No, this is how many terms. How many 2's do I have exactly? The same as the exponent. The number of 2's I have matches the exponent. So in that case, it would be the n. In other words, there's going to be an x to the n here. Don't confuse 1, 3, 5, 7 with 2 times 2 times 2 times 2. Those are kind of different animals there. The 2 times 2 part is the easiest part. But that's my numerator. What is all of this over?
N factorial.
N factorial. Okay? To make it easier, maybe write it like this. Let's move that downstairs. Now, look at the numerator. Ignore the denominator. That's there. I can't touch the denominator. It's perfect. But the numerator, oh, I erased it. The numerator, we just came up with a closed form answer for it. What is my numerator? Isn't my numerator, didn't we just figure out it was this? All still over this, by the way. A lot of stuff going on here. So now, well, how do you want to write the 2's? You have a choice. It's 2 to the n times 2 to the n. I can write that as 2 to the 2n. Oops, 2 to the 2n. Or, could I write that as 4 to the n? Which one's better? Yes. Does it make any difference which one? No. I can write it as 2 to the 2n or 2 squared to the n. Okay? It doesn't make any difference whatsoever. Just pick one. Wow. That's crazy. Now, we're still not done yet. There's one more small detail. What is that small detail? Oh, the signs are alternating, aren't they?
Yeah.
So what power of -1 am I going to have in front of all this?
To the n.
Yeah, it's exactly the same as the exponent. Wow. So now I can say that this is equal to -1 to the n (2n factorial) 2 to the 2n n factorial squared all times x to the n. Yikes. And by the way, the one that we haven't done, but I'm going to leave that up to you, is you always have to figure out what is the radius of convergence. Well, that's actually pretty easy, because the 1 plus x in absolute value still has to be less than 1 when all said and done, and that's only going to happen between -1 and 1. It's actually a very small window. Think of it this way. If x if x was a really large number, if x is a really large number, then this is going to be a very small quantity. Do you agree? But if x were a really large number, these numbers would be getting really big. Yes, they're alternating, but it's always getting bigger and bigger, which means I'm probably diverging without limit kind of ickiness. Oh, but x is going to have to be between -1 and 1. Ah, now, what if x is a really small number? A really small number. Then this quantity is very close to what? If x is really small, then what's this quantity really close to? 1. Oh, and if x is really small, then these terms are probably getting really small really fast, and okay. Yeah, so you would still do your ratio test to do all that kind of stuff. That doesn't change. Okay? But we just found a close form. Now, in every textbook that I've ever seen, and I have about 30 calculus books, and I've been a reviewer for many, I've been an editor for some when I was in school, and all of them will write the answer like this, plus dot, dot, dot. That's how the answer will look in the back of every single calculus book. It'll look like that. That's not wrong. Is that useful?
No.
Does that help you? And I have to write a computer program to actually do a calculation. I need the closed form. That's called a closed form. You know, dot, dot, dots. And if I wanted to do an expansion, could we write the first few terms if we had to? Yeah, why might that be a good idea to write the first few terms? I'm not talking about you have an exam where you have time as an issue. Why might it be a good idea to write? Let's write the first few terms out. Okay? So when n is 0, 1, 1, 1, 1, x to the 0, which is 1. Okay, I got that one covered. Minus. N is 1. 2 factorial. 2 to the second power, 1 factorial, squared, x, I'm pretty sure that's a 2 factorial over 2 squared is 1/2?
Mm-hmm.
2 over 4.
Yeah.
So this is right now minus a half x so far? All right, 2. 4 factorial, 2 to the 4th power, 2 factorial squared. Well, that would be 24 on top, 64 on the bottom, and that would reduce to, I believe, 3/8. Does that sound about right? 3/8 x squared? By the way, does that match? 3/4 divided by 2, does that match?
Yeah.
Yeah, do we need to do too many more, do you think? If it were the wrong formula, I would get no matching at all. If it's the right formula, it'll match for ever. Okay, forever. I'm done. That's enough. By the way, you can keep going. And all you're gonna do is get those guys up there. But is that important? Yeah, could I have messed that up? Oh yeah, I could have royally messed that thing up over there. But I didn't. So that's the closed form answer. Now, what if I wanted to take the derivative of this? Could I just take the derivative of this, put the n minus 1? Yes. What if I wanted to integrate that? Could I just integrate this? Yes. So far this is almost too easy. But wait a minute, we have some really serious restrictions here. I don't know if you've noticed, but right now, everything has to be in the form 1 plus x to the k. What if I wanted to do 1 plus, I don't know, x squared to the k? How did the problem start? I took a plus b to the k and I said, let's replace a with 1. Let's replace b with x. Is there anything wrong with replacing b with x squared?
No.
So what would the expansion look like, do you think? Because I want to show you, this is the tweakage. We always need to know the tweakage, don't we? Because if we don't know the tweakage, then all we can do is e to the x, not e to the thing. We can only do cosine of x, not cosine of thing. I want to be able to do 1 plus thing to the k power. So shouldn't this be 1 plus kx? Plus k times k minus 1 over 2 factorial x squared. No, x squared squared. Plus k times k minus 1 times k minus 2 over 3 factorial x cubed.
X squared cubed.
X squared cubed. Is that hard? No, that's a piece of cake. That's easy.
Negative x. And in parentheses, negative x. Yeah.
I do one right there?
1 plus k times negative x.
How about if I were like that? True statement? So now what am I going to do in the expansion? 1 plus kx plus k times k minus 1 over 2 factorial times x squared plus k minus 1, k minus 2 over 3 factorial x cubed. That tweakage was pretty easy, wasn't it? So we are allowed to do other things. Now, a little while ago, I want to take one we've already done. Actually, let's do this one. This is perfect. All right. I would like the binomial expansion for, how about 1 over 1 minus x squared under the square root? Oops. I think I erased this. Do I have to, because we just did that, do I have to start from scratch? That's not an obvious answer. You've never done the first problem. You're starting with this problem. Yeah, you got to do everything out. But now that I've done the first problem and I just showed you the two tweakages. One is change the exponent on this. By the way, we're generally not going to put a coefficient here. You can. But then the coefficients are also being raised to power, so that's not wrong. But it's just one extra thing that kind of messes it up. Changing the power, changing the sign. Both are very easy tweakages. I did both simultaneously. Here's what I'd like to be able to do. I'll write the answer. Okay.
So still.
What's going here?
Negative x to the power of 2f.
What do you think? I replaced x with the negative of x squared. Why the negative of x squared? Because it's got to be in the form 1 plus thing. So far, so good? Now, just that piece right there. Isn't that negative 1 to the n, x to the 2n?
Negative 1 to the 2f.
Okay. Is it negative 1 to the 2n equal to 1 at all times?
No.
You have an alternating series and then you made it alternate on the alternating. How in the world does that feel? I'm going to show you a simple way of thinking about it. Don't expand it. Oh, no. Isn't negative 1 to the 2n the same as negative 1 squared to the n? It's 1 to the n. That's why it's always 1. Which means that by me flipping it, it's no longer alternated. And all I did was do that. Yeah, I mean, you
Oh, you're the n factorial square. You're missing the square.
did I, I'm sorry, where?
For the series is n factorial square.
Oh, here, thank you. Yes, there's a square there. Now, we would have done this from scratch. That's what we would have done normally. But because we had just done that problem, I didn't want to start from scratch. But isn't that cool though? that's the only difference in the final outcome? Wow, I mean, that's pretty powerful. So the binomial expansion, again, it is extremely limited. I mean, it is a very special case. Would you want to do the Taylor series on this thing? Now, the Taylor series on this one would be easy. Okay, in fact, I want to go back and look at that one because that's, if this was an exam, I might word the question, give me the power series expansion for 1 over the square root of 1 plus x. Now, I would hope that you'd say, oh, that's a binomial, all I need are the coefficients, boom. Someone else might not even see that and you said, oh, I'll just do it by taking derivatives. So if my f of x is 1 plus x to the negative 1/2, then what's f prime of x? Well, that's going to be this. My chain rule factor is a 1, isn't it? Okay, so then what's the second derivative? That's going to be 3/4 1 plus x to the negative 5/2. And then my third derivative is negative 15/8 1 plus x to the negative 7/2. I keep going. Then what's f of 0? What's f prime of 0? What's f double prime of 0? What's f triple 3 slashes of 0? Well, that would be 1, negative 1/2, 3/4, negative 15 over 8. All those are true. You see those numbers up there, don't you? Now, when I'm doing my power series expansion, I'm going to then divide this by 0 factorial, by 1 factorial, by 2 factorial, by 3 factorial. Remember, you're dividing by n factorial. Problem is, do you see a pattern when we multiply things out? No. You can't see the pattern because you multiplied them out. But wouldn't that be the natural thing to multiply them out? But wasn't this just a half times 3/2? Wasn't this a half times 3/2 times 5/2? Isn't that where that came from? Oh, and that's the way we left it in this expansion. So in other words, the binomial expansion, you're probably not multiplying out the top, but if you were doing the Taylor series, you're very likely to multiply those up. So you were less likely to see the pattern. Everything we said was correct, but I'm very unlikely to see the clear pattern of the halves that we have here. Now, I said the only 2 types of problems that we use the binomial theorem for are negative integer exponents and halves. That's a pretty big restriction. But of all the fractional exponents, isn't halves the one you see by far the most often? Not just square root, 3/2, whatever. Why won't this work if I use a different, like thirds?
It has no pattern.
Well, it has a pattern, but it's a really big but, by the way. It does have a pattern. The halves, okay?
Occurring every third.
If I subtract 1 from a half, it's a half. Yeah, that's not the question. But my numerator is always going to be 2 less. It's going to count by 2s, isn't it? Right? Half, 3/2, 5/2, so on. If I do thirds, now I subtract 1, then the next one's negative 2/3, and the next one's negative 5/3, the next one's negative 8/3. Oh, okay, so I'm just decreasing my numerators by 3 at a time. How do I write that in a closed form? And there's not going to be a factorial because there's always 2 missing numbers in between, and the numbers, one's going to be odd, one's going to be even, but there's no way I can fill in the missing. Oh, but do top and bottom like you did before. Yeah, but then I still have a wonky pattern of skipping numbers. In other words, there is a pattern, it's just not a useful pattern. It's not one I can convert into factorial or exponential form. So if we had thirds, we're probably stuck with a dot, dot, dot type of answer, unfortunately. But look back in your notes. What did we do last day? Didn't we do a Taylor polynomial for cube root? And then we did an estimation. I don't remember what value we used. Something close to 1. Okay, look back in your notes. We did the cube root, and I think we only did maybe a 3rd or 4th degree Taylor polynomial. We then did an estimation of the Taylor polynomial and compared it to the cube root of the same number, and they were really, really close. Was it absolutely necessary for me to find the entire Taylor series for the cube root function? No, I only needed the first few terms. This is what you do if you need the entire series. Remember, in real life, what you usually do, you usually use the Taylor polynomial, a few terms, because they're getting so small so fast. That's going to be a huge basis of the next couple lectures. We're gonna actually do the calculations using a few terms and show how ridiculously fast things actually will converge. And I will bring things up on the computer. We'll do some of these using Wolfram because it would be too difficult for us to do the numerical calculations. But we'll do a problem where we only calculate a few terms, and we'll realize we have double-digit, right, decimal places that are accurate after just a few terms. That's why it's so powerful. That's why in reality, I do not always have to have a closed form of an answer. It's if I do, it's powerful. If for no other reason, I can program this on a computer. I can ask a computer to calculate, I don't need the infinite sum. But if I ask it to do this and I said, now computer, calculate the first 5,000, the first 5 million. It's effortless for the computer, isn't it? Because I gave it the closed form. I do this sometimes on the computer. I'll say, do the sum from this to this, and I give it a thing. What I can't do is enter several terms and then put plus dot, 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 and ask the computer to fill in all the blanks. It can't do that. It'll only do as many terms as I could physically write down. That's a very limited process, isn't it? But what if those terms I wrote down were getting really small, really fast? Then it would be okay. There wouldn't be any problem. So we're looking at both ends here. So we have to know that we're converging. Now the key is, the problem we did the other day, what was it I asked you to estimate? Cube root of what? Just go back to your last day's notes. It was the cube root of 1 point something probably. 1.2. Why was that so powerful? Because 1.2 is relatively close to 1. And so our decimal, if we had done 1.1, we would have been even closer. But what if we had done 1.9, 2.5, 3.6? It wouldn't have been very close at all because I'm getting further and further away from the number 1. So if I needed more decimal accuracy, I would have needed a lot more terms. So that only works if your calculation is close to what you're expanding by. So I gave you an example. I said, what if, and by the way, this is something that you would definitely do in a higher level course. I'm going to ask you the same problem. I want to use a Taylor polynomial, but instead of doing the cube root of 1.2, we have to understand the big picture. What did we do? How many? What was it? Third or fourth? P3 or P4?
P4.
We did P4. Does the question seem evil? Well, if f of x is x to the 1/3, before we expanded it about 1. What do you think I want to expand this one about? Expanding means where am I evaluating all my derivatives? Before we did 1. How about 8? Why 8? Because the cube root of 8 is an integer. Oh, so all of my derivatives evaluated at 8 would be rational. This would work very nicely. Let's do this problem. Because this is, I want you guys to see real life. If I said we're going to expand around 1, you go, that's so cool as long as we're evaluating near 1. What if we're not? We have options. We don't have to always use 1. 1 was just the most practical because it made finding the coefficients really, really simple. Okay, so what's f prime of x? What's f double prime of x? Triple prime of x? Fourth derivative evaluated x. This is easy. So 1/3 x to the negative 2/3. And by the way, I do not need to see a pattern of the coefficients because I'm actually only looking for the polynomial. So in this case, multiply out your fractions. Okay, so this would be what? 4/9 x to the negative 5/3. This would be negative 20 over 27 x to the negative 8/3. Does this look right? Did we do x to the 1/3 or did we do x to the negative 1/3? For some reason, I feel like the number we did was different. We did do 1/3? Positive 1/3 exponent? Oh, okay, okay. I thought I remember seeing different exponents. So, hold on, so 1/3 negative 2/3, negative, oh, that's why. I can't multiply. That's -2. Okay, my bad. I thought I remembered an 80/81, that's why. And that's gonna be the next one, 80/81, okay. Yikes. Now let's evaluate all of these at 8 and write the fraction, don't give me a decimal. A decimal in this case won't be very useful because these are rational numbers. So f of 8 is cube root of 8. F prime of 8. Well, cube root of 8 is 2. 2 squared is 4, but in this case the 4 would be on the bottom, so this would be 1/12. Cube root of 8 is 2, and I raise it to the 5th power, it's 32, but it's on the bottom, so it's 1/32, so that's now 2/288, so, I think I should have it, hold on. That's negative, that's positive, that's negative. So, make sure I got the right one, that's, okay, so that should be -1/144, there we go. So now I have 256 on the bottom, so it's, now I'll use my calculator, all right? I don't have one. Okay, oh, here it is. Then use your fraction key, folks. So you have 10/27 times 1/256. And that's 3/3456. And finally, 8, and then 2 to the 11th power, so that'd be 2048, but that's on the bottom. So 80, 81. And that one is now -5/10,368. Our final answer, we're going to give a decimal approximation. We don't want to approximate the coefficients that we use along the way because it's too much rounding along the way. So, what is my Taylor polynomial? Well, my Taylor polynomial, the cube root of x is asymptotic to, what's it going to be? That's the constant term, plus 1/12 over 1 factorial x minus 8, sorry, 12. There we go. Remember, we're expanding around 8, not around 1. Then what's the next one going to be? Plus where am I? Is that right? 3456? Hold on, something's not right there.
Okay, the derivative is 5/8.
That's not right. What should that be?
5/8.
Oh, 5, oh, I can't read my own writing. The reason I knew it couldn't be a 3 is the bottom is a multiple of 3. So that's a 5, thank you. So that's 5/3, 4, 5, 6 over 3 factorial, x minus 8 to the 3rd, and then finally minus 5/10,368 over 4 factorial, x minus 8 to the 4th. Big yikes. Now, here's what we would do. We would then say that the cube root of 8.2 can be estimated by all of these, but I'm replacing x with 8.2, which means I'd actually be calculating a 0.2 here. Okay, can we do this on our calculators? Yeah, I don't want to rewrite it. Let's just do it. And now we leave the decimals. So, 2 plus 0.2 divided by 12 minus 0.2 squared divided by 144 divided by 2 plus 0.2 cubed times 5 divided by 3, 4, 5, 6 divided by 3 factorial minus 0.2 raised to the 4th times 5 divided by 10, 368 divided by 4 factorial. All right, has anybody got an answer? And cheap calculators are so much faster. I don't know if I'm even close. This is what I got. Anybody else get that? Any confirmation? That's what I just did this calculation replacing x with 8.2. And this is what my calculator spit out. Is this a rational number? Yeah. Well, look at this denominator, if you will. I have 0.2 to the fourth power. That's 1/5, if you will, to the fourth power. That's 625. This denominator is really big about right now, isn't it? Which means the effect this one's going to have is way, way, way out there. How do I know that? Because now I'm going to do the cube root of 8.2. And my calculator's telling me that this is 2.016529675. My calculator only gives me this many decimals. And I do believe that's exactly the same answer. Is that good? That's really good. Would I have gotten the same answer if I only went this far? Maybe. I don't know. So let's just calculate the effect this guy had. What is this number right here? Let's just do it. So it'd be 0.2 raised to the fourth power times 5 divided by 10368. It's pretty small, but I think I still needed it. Okay, so does it matter that we didn't expand around 1? No. Would you say this was a little bit more work than the other one was? Yeah, because the coefficients were ickier, but they're still rational numbers. You are doing this to do an estimation. Well, why would I do this? I have technology on my side. I have calculators. Because sometimes we may want to integrate something. We may want to integrate something that doesn't have an antiderivative. Well, what do you mean we want to integrate something that doesn't have an antiderivative? You all told me the answer to this question. Let me put a K on here. Do we know what the answer to this question is now? Yeah, it's the answer to our old question, but instead of x to the n, it would be x to the kn. And that's a polynomial. I can work with that one easily. I can differentiate that one. I can integrate that one easily. Integrate this one. Well, there's a couple of k's that I can do that for. I can do that if k is 1. I can do that if k is 2. I can do both of those. K is 2, we'd have to do a trig substitution. K is 1, it's a simple u sub. For every other value of k, there's no antiderivative. Period. But there's an infinite number of k's, and none of them can be integrated. That's my whole point. Take something easy, tweak it a little bit, and you can make it impossible. Yet we can still work with it because we dealt with it as a series. That's why series are so important. I can do things that I can't do otherwise using series. No, but I'm not going to get the exact answer. Do I have to get the exact answer? We did a 4th degree polynomial and we literally got the exact answer. Oh. Starting to get the point here. It's unbelievably powerful with what we can do with these three. I'm not going to ask you this question generally. I want you to understand, though, this is a totally valid question. We chose to expand around 1 because all the derivatives were easy around 1 because we couldn't use 0. Remember, you always use 0 unless you can't. And if you can't, you can probably use 1. Technically, you can use any real number that the function is analytic at, but you only want to use numbers that give your derivatives easy calculations. Otherwise, you're making the problem way too hard. Okay? Chase,